Dear students, today we will discuss Theorem 1.38. Suppose sequence Fn is a sequence of complex measurable functions defined almost everywhere on X such that summation n varies from 1 to infinity, integral over X, mod Fn d mu is finite. Then the series f of x is equal to summation n varies from 1 to infinity fn of x converges for almost all x. Also f belongs to L1 of mu and integral over x f du mu equal to summation n equal to 1 to infinity integral over x fn d mu. Okay, so this is the statement of the theorem. So what this statement says, suppose we have a sequence of complex measurable functions defined almost everywhere, okay, on X, where X is the measurable space with sigma algebra scriptum and measure mu, such that summation n varies from 1 to infinity integral over X mod fn d mu is finite or converge. Then this sum of functions, okay, they themselves converge almost everywhere, and the limiting function f to be in L1, okay, and whose integral is the sum of the integrals of fn's. Okay, so this is what the theorem says. So now look at the proof. So let Sn be the set on which Fn is defined. Okay, Sn be the set where the function Fn's are defined almost everywhere. Okay, so which means whenever we have Fn's, okay, and they are not defined in Sn complement, okay, that will have a measure 0. That means suppose we have f1, f2, f etc. Then for f1 we have a ns1. Okay, so on s1 f1 is defined. Okay, and f1 is defined almost everywhere. That means there exists a s1 complement on which measure of s1 complement is equal to 0. Okay, so we have mu of Sn complement equal to 0. Okay, now consider the function psi of x, which is equal to summation n varies from 1 to infinity mod fn of x for x belongs to S, where S is the intersection of Sn's. Okay, so then this psi can be viewed as a function defined on S. Psi of x means summation mod fn of x. Okay, so psi of x is be a measurable function defined on S, where S is the intersection n varies from 1 to infinity Sn. Okay, now then we have mu of S complement equal to 0. Okay, then by the theorem 1.27, what 1.27 says, this is the the theorem 1.27. okay, that means if we integrate the sum of positive functions, okay, then we can interchange the sum and integral. That's what this theorem says. So by using this theorem we can interchange. So we have integral over s psi d mu, that means integral over s, psi means summation n varies from 1 to infinity mod fn of x. So by using that theorem we can interchange. So this is equal to summation n varies from 1 to infinity integral over s mod fn of x d mu. Okay, so what is this by our hypothesis? So summation n varies from 1 to infinity integral over x mod fn d mu is finite. Okay, but here we have integral over s. So we have integral over s summation n varies from 1 to infinity mod fn of x, which is equal to, we interchange sum and integral, so which is equal to summation n varies from 1 to infinity integral over s mod fn d mu, which is less than or equal to summation n varies from 1 to infinity integral over x. Okay, previous it was s, then which is less than or equal to summation n varies from 1 to infinity integral over x mod fn d mu. So by hypothesis, which is finite. Okay, so that means this is less than infinity, and therefore we have integral over s psi d mu is finite. Okay, so here we have psi is a positive function whose integral is finite. Okay, hence psi is finite almost everywhere on s. Okay, now if e equal to set of all x belongs to x such that psi of x less than infinity, that means we have our x. Okay, and this is our s, so this is our s complement. Here we have measure 0, and on s this psi is finite. Okay, psi means this one, summation mod fn of x. So here we have summation, this is actually psi equal to mod fn of x is finite almost everywhere. So that means there is a sum f here, okay, on which mu of f equal to 0, measure of f equal to 0. Okay, so we take this as e. So we have here measure is 0, here also measure is 0. Okay, then the union f union s complement, there are also measure, that is mu of s complement union f also 0. Okay, so we take this as e, this is our e. Okay, so e is the set of those elements in s such that psi of x is finite. Okay, here we have this psi is finite. Okay, for all x here. Okay, so we have absolute convergence. Okay, so this implies the usual convergence, and therefore summation fn of x converges almost everywhere. Okay, so we have this fn of x converges almost everywhere. Now we want to show f belongs to L1 of mu. Okay, here it is easily observe that f belongs to L1 of mu. Why is that? Because we have summation mod fn of x is integrable. Okay, that means integral over s summation n varies from 1 to infinity mod fn d mu is finite. This is already we have seen. That means integral over s psi is finite d mu. Okay, so this means that psi belongs to L1 mu. Okay, and this function is bigger than f. That is, we have mod f less than or equal to summation mod fn, and therefore we have mod f of x which is less than or equal to psi of x. Okay, and therefore f belongs to L1 of mu. Okay, so we have this. Now it remains to show that integral over x f d mu equal to summation n varies 1 to infinity integral over x fn d mu. Okay, for proving this part we will use dominated convergence theorem. Okay, so on that we take gn as gn equal to f1 plus etc plus fn. Okay, and also what is mod gn? Mod gn which is less than or equal to summation mod fn. That means xi. This belongs to L1 of mu. Okay, so and also we know that gn converges to f almost everywhere. Okay, then so we take this as the dominating function. This is the dominating function. That means our psi. Okay, then we apply dominating convergence theorem to conclude this proof. This is for all x belongs to E. Okay, thank you.